So, in this session we are going to learn the Ginzburg Landau theory. Of superconductivity. Remember, this was evolved before the microscopic theory, that is BCS theory, was put forward, and it is a phenomenological theory of second order phase transition, which was extremely successful in describing a few properties of these superconductors, such as the penetration depth and the coherence length, and thereby a ratio of them could be formed which helps in distinguishing between type 1 and type 2 superconductors. So, in 1937 Landau proposed a theory for second order phase transition. Now, by second order phase transition, what we mean is that involves latent heat. This is one of the modern definitions of phase transition. In this theory, there is an order parameter that continuously vanishes across the phase transition. So, this order parameter is non-zero for t less than T c, and it is equal to 0 for t greater than T c. So, this is an indicator of the phase transition. Say for example, in a paramagnet to a ferromagnet transition, the magnetization can be the order parameter. So, the magnetization let us call it by m. So, magnetization is not 0 for t less than T c, which talks about a ferromagnetic state, and magnetization being 0 for t greater than T c. So, this is a ferromagnet and this is a paramagnet. Similarly, in superconductors, we can talk about the energy gap of the excitation spectrum. This can be taken as the order parameter, call it as delta, and delta is not equal to 0 for t less than T c, where T c is the transition temperature for a superconductor, which is a characteristic of a material. So, this corresponds to a superconducting state, and delta equal to 0 for t greater than T c. This is called as the normal state or a non superconducting state. Now, since the order parameter continuously evolves across the boundary of the phase transition, it should be possible to write down the free energy as a power series in the order parameter. So, this is the whole idea of GL theory, Ginzburg Landau theory, I am abbreviating as GL theory. So, it says that free energy should be expanded in terms of order parameter powers of in terms of power series of order parameter. Now, it can be noted that free energy is a scalar. However, the order parameter can be higher dimensional quantity such as a vector or a tensor or a complex quantity. So, this is what we are going to do, that is write down the free energy functional. The meaning of the word functional is function of a function. So, we will write this free energy functional, which is a function of the order parameter, and order parameter could be a function of say the spatial parameter such as r or or any other parameter that is relevant to the problem. It is usually the space variable which is taken as that the order parameter being a function of that. Now, we will study the GL theory. So, the order parameter in GL theory is the wave function of the so called super electrons. Okay. Call that as psi of r, such that the density of the super electrons, what I mean by super electrons is that they are superconducting electrons. Which is equal to mod psi r square. So, the plan is like this, that we will do two cases. One is absence of an external field, magnetic field, and then also we will do it in presence of an external magnetic field. And finally, we would compute two different quantities. One is called as the coherence length, and B called as the penetration depth. So, the free energy in H external equal to 0. So, there is no external field, and we write down the superconducting free energy, which is equal to free energy of the normal state plus alpha psi mod square plus a beta by 2 psi to the power 4. Note that we are keeping the expansion only up to the biquadratic, that is quartic terms of psi, and the other thing is that there are no odd powers of psi involved, because that would be antisymmetric with respect to the change in the order parameter. So, Fs is free energy of a superconductor, Fn free energy of a normal metal, and alpha and beta are phenomenological coefficients expansion coefficients so minimum of Fs. So, we want to minimize the free energy with respect to the order parameter and find out where the optimum value which minimizes the Fs lies. Minimum of Fs is obtained by taking a dFs d psi equal to 0 and this is equal to a 2 alpha psi and plus 2 beta psi cube. So, I can take a psi common and this becomes equal to a 2 psi common and this will be like a alpha plus beta. Psi mod square that does minimize this, let us write it with a psi 0 mod square equal to minus alpha over beta. Thus, we can write down f n minus f s it's equal to alpha into alpha by beta and minus beta by 2 alpha by beta whole square. This becomes equal to alpha square by 2 beta. And it is almost obvious that alpha and beta both could be temperature dependent. Now, in the first term, so let's write this once more that Fn minus Fs is alpha square over 2 beta, Fn minus Fs equal to alpha square over 2 beta. So, in the first order, that is not too far from Tc, that is at temperature which is not too far from Tc, alpha can be T minus Tc. The reason is that alpha equal to 0 at T equal to Tc, alpha is less than 0 at T greater than Tc and alpha is greater than 0 at this is T less than Tc and this is T greater than Tc. Okay. Now, this happens because psi is equal to 0 for T greater than Tc. So, psi must be going as a Tc minus T whole to the power beta and whole to the power half here for T less than Tc. So, the important thing for us to understand is that alpha changes sign across the phase transition However, beta should not change sign, because if both of them change sign, then of course we will not have this equation valid, which is psi mod square equal to minus alpha by beta. And moreover, beta also should not have any temperature dependence, so that we will have some pathological. So, if beta has to be if beta does not have to change sign across the transition, then it has to be like T minus T c whole square, because a whole square does not change sign. But in that case, your alpha by beta will be like 1 over T, which would be divergent as T goes to 0, and that should not happen. So, beta should be a constant. So, basically it is a positive constant and independent of temperature. Of course, it means that being constant means that it is independent of temperature. So, at least for small deviations from T equal to T c, this is what should happen. So, alpha has a form which is like A T minus T c, beta is a constant, and hence we will have the psi mod equal to 0 for t greater than T c and psi mod equal to going as T c minus t whole to the power half with a's and b's as constant. A is a constant here. Now, consider a superconductor in an external field, magnetic field that is. So, the way it is taken care of is that the momentum is changed by P minus E A by C. This you must have seen in your classical mechanics course when we talked about a charged particle in a magnetic field. Now, this A is the vector potential which is related to the field as H of R external equal to curl of A. So, it is always derivable from a vector potential by this relation. This tells that the del operator should be replaced in presence of a magnetic field by this. Now, the free energies have to be written down, the same free energies that we have written down earlier. So, F s equal to a F n plus alpha psi, because of the magnetic field now which is a function of R, we have an inhomogeneous order parameters. Now, psi starts depending upon R. And also because of the magnetic field, we have an additional term which is given by I E by H cross C A of R and then a psi of R mod square and plus a magnetic energy because of the external field which is given by H external square by 8 pi. Now, free energy F is a functional of psi of R, psi star of R, del psi of R, del psi star of R and A of R. So, minimizing it, psi star R, we have del F s equal to minus of H square by 2 m del minus I E by H cross C A of R square psi of R plus alpha psi of R plus beta mod psi R square psi of R, and we can still write this as the other term which is H external, which we do not need to worry about. So, let us just write it as H external square over 8 pi. Right now, ignore this term. It is not that it is not important or it is small, because we do not need it for our discussion now. So, we ignore that, and this when we put this quantity del Fs equal to 0, that would tell that these bracket has to vanish, this curly bracket has to vanish for delta Fs to be 0, this bracket will be equal to 0, and hence we get the first Ginzburg Landau equation as this. So, note the difference between the earlier case when we do not have magnetic field is that psi was homogeneous. We could mention that here as well, that psi is and does not depend upon R basically. So, this is called as a first GL equation, and in which we have neglected the second term there. Now, to get the second GL equation, minimize Fs with respect to A, the vector potential, and that gives a very familiar equation which is called as the Amperes Law, which is like this. So, this is the second GL equation, where your Jr has to be identified as so, that is the second GL equations, and let us now talk about the boundary conditions. And in doing so, we would get, or we would sort of obtain the relations or the expressions for the penetration depth and the coherence length. So, let us talk about an inhomogeneous order parameter, which we have been talking about since we have introduced the magnetic field. So, let us consider a half region of, so this is x equal to 0. So, this is where the superconductor exists. So, superconductor exists for x greater than 0, and x less than 0 we do not have a superconductor. It could be a normal metal or it could be a magnetic metal, for example. So, there is a non-superconductor. We will just simply write it as non-superconductor. So, these are junction systems which are routinely studied in experimental physics, experimental condensed matter physics, and one can easily make a junction of a superconductor and a non-superconductor. Now, for deriving the expression for coherence length, put A equal to 0. So, we do not need the external field there, and in that case I get from the first GL equation and the variation is taken to be in one dimension. So, this is the x axis, alpha psi plus a beta psi cube, this is equal to 0. So, we have said that earlier that alpha is negative in the superconducting state. So, take alpha to be equal to minus alpha and define a quantity called as xi, which is called as the coherence length, and this is equal to h cross square over 2 m alpha. Also, this is simple algebra. Also write equation, let us call this as the first one as equation 1, first GL equation, the second GL equation to be equation 2 and this to be equation 3. So, now write equation 3, in addition define that beta over alpha psi square is equal to f square. So, with these definitions one can write down equation 3 as minus xi square f double prime minus f plus f cube equal to 0. So, I have cast this first GL equation in terms of a scaled variable which is called as a f. Now, multiply by f prime which is equal to df dx, and then one should be able to write this as d dx of minus psi square f prime square over 2 minus half f square plus 1/4 f 4, this is equal to 0. So, if d dx of this equal to 0, which means that this should be equal to a constant, now far from the boundary, that is into the superconducting state. So, this is the boundary, and if you are too much into the superconducting state, f prime should be equal to 0 or psi prime should be equal to 0. So, the variation of the order parameter with as a function of x should be equal to 0, and hence this gives that f square should be equal to 1 which tells that psi square should be equal to alpha over beta, which is what we have obtained. Then this equation, which is equation 4, becomes a xi square f prime square equal to half 1 minus f square square. So, this is the equation for psi or f which needs to be solved, and the solution is of this form, that f of x equal to tan hyperbolic x by root 2 psi. So, that gives that psi equal to alpha by beta whole to the power half tan hyperbolic x by root 2 xi. So, that tells that psi as a function of x has a variation like this. So, that gives the extent of the wave function for the Cooper pair or the super electrons, and there is a characteristic length that emerges which is equal to xi. So, xi is the measure of the distance over which the order parameter responds to a perturbation. In this case, the perturbation is the presence of a boundary that lies between the superconductor and maybe a normal metal. Again, since alpha equal to A T minus T C, the temperature dependence of the coherence length, so this is called as the coherence length. So, xi of t is equal to h cross square over 2 m a T c and 1 minus T by T c whole to the power minus half. So, xi t diverges as 1 divided by 1 minus T by T c whole to the power half. So, as t goes to T c, this diverges in this fashion. You can see clearly that the divergence is like a square root divergence. So, this is the behavior of the coherence length. Let us look at the other quantity, which is the penetration depth. Look at this expression, the second GL equation. If you drop the first term and only look at the second term, that is this term, let me just mark it in red. So, if you look at this term, then this exactly looks like the London equation, without the first term, that is the usual current term. So, we are purely looking at the current due to the external field, and then it looks like that J of r is simply 4 pi by C 1 by lambda L square A of r, and immediately the lambda L can be read off as m c square divided by 4 pi E square and mod psi square, and this so this is the vanishing, or rather the dependence of psi. So, the space dependence of psi will yield the space dependence of lambda. Remember, this psi actually falls off as tan hyperbolic x over root 2 xi. So, that will determine that how lambda L falls off as a distance. And to look at the temperature dependence, the lambda L, which is equal to m c square beta divided by 4 pi E square A T c 1 minus T by T c whole to the power minus half. So, this is lambda L as a function of T, this is the penetration depth. So, lambda L T diverges again as 1 by T my T c whole to the power minus half, exactly like xi of T, and one can also define a dimensionless parameter called as lambda by xi, which now becomes equal to m c over E h cross beta over 2 pi whole to the power half, which has only one unknown parameter, which is beta, which appears in the Ginzburg Landau theory. Now, we know that kappa greater than 1 by root 2 is termed as the type 2 superconductors. And less than 1 by root 2 as the type 1 superconductors. So, to summarize that without doing explicitly a microscopic theory, which we have done for the BCS case, here simply writing down the free energy functional as in powers of the order parameter and minimizing it with respect to the order parameter, one can actually get the two energy scales that are relevant for these superconductors, namely the penetration depth and the coherence length, and not only that, their how they diverge for T close to T c is also obtained, which are of this order as 1 by T minus T c whole to the power minus half. So, to conclude the chapter on superconductivity, we have given one a historical introduction, and then we have said about properties such as zero resistance, Meissner effect, etc. And then we have talked about the origin of the attractive interaction between electrons mediated via phonons this is known as Cooper's instability, and then of course, we have done BCS theory, and in which the gap, superconducting gap is obtained. And the superconducting gap is seen to be non-analytic in powers of the strength of the attractive electron-electron interaction. So, one cannot do a perturbative theory in order to get this result. Then we have done a variational theory and also gotten the behavior of the superconducting gap as a function of temperature. And then finally, we have done a Ginzburg Landau theory to obtain one coherence length and two penetration depth. and these are all required for you to learn, because this story of superconductivity is fairly old. Now, you understand it is more than, it is about 110 years old since it is first discovered, and then also it was a new class of superconductors were discovered in 1986, and a large amount of work had gone in since then. However, we have not touched that part because of poor knowledge or still evolving knowledge in that particular area, but we have done these studies of the weak coupling superconductors, so called the BCS superconductors, in somewhat details.